10 Temperature Rise Indications. A 2015 post warned about a possible 20 degrees Celsius global temperature rise by 2054. An earlier version of the background image was posted in 2013. Indeed, politicians have ignored these warnings for almost a decade now and, in some respects, the warnings were actually too conservative, as the above image may have given the wrong impression that we had until the year 2054 to achieve the necessary action, whereas over the years indications have become ever stronger that a huge rise could take place over a few years and result in a rise of more than 18 degrees Celsius as soon as in 2026. Let's go over the 10 most critical indications again. 1. The trigger, El Nino and sunspots. A huge temperature rise in the Arctic looks set to unfold due to the combined impact of an upcoming El Nino and higher sunspots, which could be the trigger for loss of the latent heat buffer, and albedo losses due to further sea ice decline, as further discussed below. As temperatures keep rising in the Arctic, changes to the jet stream look set to intensify, while loss of terrestrial albedo in the Arctic could equal the albedo loss resulting from sea ice decline. Meanwhile, rising ocean heat and greenhouse gases are already reaching critical levels, especially in the Arctic. 2. Ocean heat. An image is added showing a trend, based on 1880 to 2020 data, for sea surface temperature anomalies, versus the 20th century average, on the northern hemisphere. Note that the image indicates that the latent heat tipping point was crossed in the year 2020. Keep in mind that the above image shows sea surface temperature anomalies, which are suppressed during a La Nina period. We're currently in the depth of a persistent La Nina. Underneath the sea surface, though, temperatures are rising fast, which could be even more critical than the temperature rise at the surface, the more so since a freshwater lid appears to be forming at the ocean surface that enables hot water to dive underneath this lid and underneath the sea ice, and enter the Arctic Ocean. 3. Jet stream. As temperature in the Arctic rises, the jet stream changes, resulting in more extreme weather and enabling cold air to leave the Arctic and warmer air to enter the Arctic. This, in combination with the freshwater lid on top of the North Atlantic, can cause ocean heat to build up in the Atlantic Ocean, to suddenly be pushed along the path of the Gulf Stream at high speed into the Arctic Ocean. 4. Latent heat. The amount of energy absorbed by melting ice is as much as it takes to heat an equivalent mass of water from 0 to 80 degrees Celsius. As the temperature of the ocean rises, ever less sea ice remains in the Arctic. Once the sea ice is gone, further heat arriving in the Arctic Ocean will strongly raise the water temperature and the atmosphere over the Arctic Ocean. A trend based on Pyoma's data points at zero Arctic sea ice volume by September 2027. 5. Methane. The methane hydrates tipping point is estimated to get crossed as ocean temperature anomalies on the northern hemisphere become higher than 1.35 degrees Celsius above the 20th century average, as the image further above indicates. This could result in mass releases of methane from the seafloor. While seafloor methane could already start erupting in large quantities beforehand at vulnerable locations. 2 images show high methane levels that have recently been recorded at Mauna Loa, Hawaii, and at Barrow, Alaska. 6. Carbon dioxide. NOAA data show a carbon dioxide, CO2, level of 421.13 parts per million, ppm, for the week starting May 8, 2022, a new record high since measurements started at Mauna Loa, Hawaii. Carbon dioxide levels are even higher over the Arctic. Very high carbon dioxide levels were recorded recently at Barrow, Alaska. To find historic CO2 levels this high, we'd have to go back millions of years. There are 2 things that are delaying the temperature rise: oceans due to their mass take years to heat up, and sea ice acts as a buffer, consuming ocean heat in the process of melting. 7. Albedo change. Without sea ice, less sunlight will be reflected back into space, and will instead be absorbed by the Arctic. Sea ice reflects 50% to 70% of the incoming energy, while thick sea ice covered with snow reflects as much as 90% of the incoming solar radiation. The ocean reflects only 6% of the incoming solar radiation and absorbs the rest. 8 Emissions from what used to be permafrost. Permafrost degradation, both terrestrial and on the seafloor of the Arctic Ocean, looks set to cause huge releases of greenhouse gases, particularly CO2, CH4, and N2O, in turn also causing more water vapor to enter the atmosphere, causing a huge rise in temperature, especially in the Arctic, where vast amounts of methane are contained in sediments at the seafloor. 9 Loss of aerosol masking effect, rise of black carbon. A further rise in temperature to rise looks set to unfold due to the falling away of sulfate aerosols, while there could be a further temperature rise due to releases of other aerosols that have a net warming impact, such as black and brown carbon, which can increase dramatically as more wood burning and forest fires take place. 10 Clouds feedback. As the temperature keeps rising, this will trigger further self-reinforcing feedbacks such as an increase in water vapor combined with a decrease in lower clouds decks, further increasing the temperature. Joint impact. There are further tipping points such as the collapse of biosystems and loss of carbon sinks and, importantly, there can be a lot of interaction between them. Altogether, the temperature rise by 2026 could be more than 18 degrees Celsius compared to pre-industrial. From the set at https://www.facebook.com/samcranas/post/101